Good afternoon. We are going to dive into section 10.4. So last time we talked about the dot product of two vectors, and we learned how the dot product produces a scalar. Today we're going to talk about the cross product of two vectors, and we're going to see that cross products produce vectors. And so given a three-dimensional vector A and a three-dimensional vector B, the cross product, which we write like this, we use the little time symbol there. It's this new vector, and it's defined as follows. And it's kind of an intimidating formula. I'll show you a shortcut in just a minute of how you can actually compute with it. But for now, notice that in the first component, there's no ones. It's all the twos and threes. And the way that I've written it, you've got A, the first vector, is always first. So it's is always starts out smallest. So A2, B3, and then minus, you flip it, A3, B2. Second component, there's no twos. A starts out with a smaller number, so A1, B3 minus A3, B1. The difference is I threw a negative on the front. And then the last component, there's no threes. A starts out smaller, A1, B2 minus A2, B1. So that's the formula. Let me introduce to you some notation that you may have seen if you've had linear algebra. If you have a grid of numbers, A, B, C, D, so these are four numbers written in a grid like this, their determinant is this diagonal minus this diagonal. It's the product AD minus the product BC. We won't typically write these bars when we're working these out, but I just want you to see them so that you know what they mean. All right, so let's actually work out an example. How do you actually do this in practice? Here's how I do it. I actually write down my two vectors like this. I write down 1, 2, -1, and then I'll write below it 2, -3, and 5. And now when I want to come over here and actually compute this guy, I know the first component, I'm going to cover up the first components, and I'm going to take this diagonal minus that diagonal. That's all this part is. It's just a determinant of this grid. So you look at that group of numbers and you say 10 minus 3. And so I'll actually write out the details so you can see it. You get 10 minus 3. For the middle component, you throw a negative in there, and then you do the same thing. You cover up the middle, and the numbers that are left form a 2 by 2 grid, and so you're going to get 5 minus -2. So I get a 5 minus -2. That's the middle component. The last one, I'm going to cover up these guys, and then I get what? -3 minus 4. So this is -3 minus 4. Let's clean this up now, and we get a 7, and then we get a -7, -7. So that's the cross product. So I would like to invite you to pause the video and work out the following problems. And now the way I've done it, you can't see the original vector, so let me copy those for you, and then I'll drop them in right here. And I would like you to pause and then compute these four things. You're going to compute two cross products, and then you're going to use the cross product that I computed and the one that you did here to take these two dot products as well and see what you get. Go for it. All right, so you should have gotten -7, 7, 7 for this one. You should get the scalar 0 for these two, and you should get the vector 0 for this. And hopefully you noticed that this is exactly negative what we got when we computed A cross B. So hopefully you're wondering, is that always true? It's interesting when you think about A cross B dot A, what is the significance of this dot product being 0? Well, it means that these two vectors are orthogonal. And so you can think about, in this example, this part is actually saying that the cross product is orthogonal to both A and B. The cross product of A and B is orthogonal to A and B. And then finally, we notice that A cross A is 0. And you cross a vector with itself, at least in this case, we got 0. So, of course, we're all wondering now, are these always true or not? What's the story? And so let's write that out. So here is the facts that you need to know. So the first fact is that A cross B is always negative times B cross A. That's kind of nice. The second is that A cross B is always orthogonal to both A and B. We'll talk about this part more in a few minutes, but the point is anytime you dot A cross B with either one of these, you know the dot product is 0, and geometrically if you have A and B, then A cross B is going to be perpendicular to those two. And finally, it's always true that A cross A is the 0 vector. Now do be careful, cross products give you vectors, so this is the 0 vector, not the scalar 0. Very good. Well, let's end this video here, and in the next video we'll talk a little bit about the orthogonality here.